Hello everyone. In this class we are going to see theorem number 14. The statement is if f and g belongs to the Riemann integral of a comma b, then we got to prove that the multiplication fg also belongs to the Riemann integral a comma b. What is the given information? That they've given that f comma g belongs to closed interval of a comma b. So now to prove f and g also belongs to the Riemann integral of closed interval ab, we got to consider one condition that we have earlier proved, that is f plus g also belongs to the closed interval a comma b. As f plus g also belongs to the R closed interval a comma b, and we have another theorem that is f minus g also belongs to R of a comma b. As f plus g and f minus g both belongs to the Riemann integral of a comma b, its square also belongs, because as f belongs to R over a comma b, we can tell that f square also belongs to R over a comma b, right? So from that theorem, we can tell f plus g whole square also belongs to R over a comma b. Then in the same way, f minus g whole square also belongs to R over a comma b. If this belongs to the Riemann integral and this belongs to the Riemann integral, it's subtraction. That is f plus g whole square minus f minus g whole square also belongs to the Riemann integral of a comma b. What is f plus g whole square and f minus g whole square? You will be having f square plus g square plus 2fg minus f square minus g square minus 2fg. Sorry, minus into minus plus. So f square g square gets cancelled. You'll be having 4fg. Okay. So in the next step, we can conclude that this 4fg also belongs to the Riemann integral of a comma b. Then, as this is a constant term, we can tell f into g belongs to R over a comma b. So what is that we have took? We have took if f comma g belongs to the Riemann integral of closed interval a comma b, then we have proved f into g, that is the multiplication also belongs to the Riemann integral of a comma b. Now next we will be looking into the definition, that is continuous function. So what is the definition of continuous function? As I've already told earlier in the Rolle's mean value theorem, by the graph, if the graph is continuous like this without any breaks, then it is known as continuous function. So now what is the exact definition of continuous function? We will look into it. So f of x is said to be continuous at a point A. Whenever we define a continuous function, we will be defining at a particular point A. So if for all epsilon greater than 0, there exists some delta greater than 0 such that mod f of x minus f of a is less than epsilon whenever this mod x minus a is less than delta. So for every domain, there will be some image which is strictly less than epsilon. We have to put this into mind. So for this can be symbolically written as limit x tends to a, f of x is equals to f of a. Am I clear till here? Next, moving on to the next definition, that is uniform continuity function. What is uniform continuity function? A function f is said to be uniform continuous if for all epsilon greater than 0, same thing, there exists a delta greater than 0 such that mod f of x1 minus f of x2 is strictly less than epsilon whenever mod x1 minus x2 is less than delta. So for every domain, there will be a image which is strictly less than epsilon. So I hope I'm clear with the definition of uniform continuous and continuous function. Now let's move into the other theorem, that is, which says if f is continuous, then we have to prove that whether f is Riemann. This is a very important, very important theorem. They're asking if f is continuous on closed interval a comma b, then prove that prove that whether f is Riemann integrable over a comma b or not. So to prove whether it is Riemann integrable, what is that we have to take? We have to take partitions, then we have to define the subintervals and all. So proof, given that f is continuous, given that f is continuous on closed interval a comma b, right? If f is continuous on closed interval, and we know that every continuous function is bounded, so we can write f is bounded on closed interval a comma b. Now, as we are talking about Riemann integration, we have to define partition. So what is that? Let p is equals to a equals to x naught, x1, and so on up to xn, that is equals to b. So this is partition of closed interval a comma b. Okay. Now what is the, as we have defined the xn, what is the rth subinterval? Ir is equals to xr minus 1 comma xr. And what will be the length of the subinterval? The length is defined as delta r. What is delta r? B minus a. Now let us define, as f is bounded on each IR. F is bounded on each IR. Now we will be defining infimum and supremum. So how will we define infimum and supremum? Small mr and capital MR. Let this be infimum and supremum. Let this be infimum and supremum of F on IR. That is the subinterval IR. And then we will be, and we already know that by uniform continuous function, what is the definition of it on the rth subinterval? We can tell that for all epsilon greater than 0, there exists some delta greater than 0 such that mod f of x1 minus f of x2 is less than epsilon whenever mod x minus x1 is strictly less than delta. Okay, so as we have to consider this as epsilon by b minus a. The reason we will be considering b minus a is because I'll be telling you at end, only because to get less than epsilon we have to divide it by b minus a. So this is mod x1 minus x2, which is strictly less than delta. Let this be relation 1. Next, moving on to the next step, that is, here we already know that f is bounded, where f is bounded on closed interval a comma b, right? F is bounded on closed interval a comma b, and we got to take this in such a way that there exists some x1 x2 belongs to, as we already know, x1 comma x2 belongs to some subinterval IR. So I'm taking this f of x1 as some in supremum and f of x2 as some infimum. Okay, we are just considering x1 x2 are some elements in subinterval IR. So I'm just taking that as supremum and infimum. Now what is capital MR minus small mr? This is equals to mod of f of x1 minus f of x2. Okay, so what is x1 minus x2 actually from the previous slide? F of x1 minus f of x2 is less than epsilon by b minus a. And I told you to remember why did we take b minus a, I'll tell you at the end. Okay, this is since from 1. As we have considered f of x1 minus f of x2 less than epsilon by 2, epsilon by b minus a. Now let us consider what is the condition to be integrable. To prove it is integrable, we have to prove that UPF minus LPF is strictly less than epsilon. Okay. So what is UPF and LPF? What is UPF? Summation r equals to 1 to n capital MR into delta r minus summation r is equals to 1 to n small mr into delta r. From this we got to take delta r common. So you'll be having r equals to 1 to n capital MR minus small mr into delta r. this is equals to summation r equals to 1 to n. What is capital MR minus small mr? What is this? Less than epsilon by 2. So this is less than epsilon by b minus a into delta r. You have to write as it is. So this will be less than, as this is with irrespective with r, you got to take that out. So epsilon by b minus a, which summation r equals to 1 to n delta r. So this is less than epsilon by b minus a, that is epsilon by b minus a into b minus a. So b minus a gets cancelled. This is strictly less than epsilon. So to get this is strictly less than epsilon, we got to divide this by b minus a. That is just modifying the epsilon. So we can tell that as UPF minus LPF is strictly less than epsilon, you can strictly tell that f also belongs to r over a comma b. Okay, this is finished. Now looking on to the converse of this theorem. So what will be the converse of this theorem? That is, if f belongs to r over a comma b, then f need not be continuous, on closed interval a comma b. So to prove this statement, whether it is correct or not, I just wanted to give you an example. For example, let us consider if f of x is equals to some x, some closed interval x, then f is Riemann integrable. Then f is Riemann integrable on closed interval a comma b. But f is not continuous at x is equals to 0. But f is not continuous, at x is equals to 1, which belongs to 0 comma 2. Due to the following, why this like, as f is not continuous at x equals to 1, we will prove why it is actually not continuous. The first one is, you got to prove left hand continuous and right hand continuous. So x belongs to 1 minus f of x. What is x belong, limit x tends to 1 minus f of x? This is limit x tends to 1 minus closed interval x. So if you put h minus this thing, so you'll be having 0 over here. Why? Because when we solve continuous problems, what is that we took? In place of x, you got to substitute a minus h or a plus h, where limit h tends to 0. Okay. So this limit h tends to 0 at f of x. Now limit x tends to 1 plus. What will that be? F of x is equals to limit x tends to 1 plus closed interval x. So this will be a plus h, that is 1 plus 0, this will be equals to 1. So this limit and this limit are not equal. So limit x tends to 1 minus f of x is not equals to limit x tends to 1 plus f of x. That means we can tell that if right hand and left hand are not equal, so this is not continuous. I hope I'm clear with this. And there is another note point. The note point says, note, if f is mapping from a comma b to r, Riemann integrable r, this is discontinuous. This is discontinuous, right? If f is mapping from a comma b to r, which is discontinuous at finite number of points, okay, if f is mapping from a comma b to r is discontinuous at finite number of points on closed interval a comma b, then f belongs to r over a comma b. For example, f of x is equals to some closed interval x, then f is discontinuous at x is equals to 1, 2, 3. Since or therefore f is Riemann integrable on 0, 4. This example, whether it is continuous or discontinuous. Next, we will be looking into another theorem, a very important theorem. This theorem states, this is also very important one. So the theorem statement is, if f is monotonic on a comma b, if f is monotonic, if f is monotonic on closed interval a comma b, then they are asking us to prove that then f belongs to R over a comma b. If f is monotonic on a comma b, then f belongs to R over a comma b. Proof. So how will we prove that? Write down the given information. What is that they gave? F is monotonic. F is monotonic on closed interval a comma b. On closed interval a comma b. This, what is monotonic? Either an increasing function or decreasing function is known as monotonic. So this implies f is either increasing or decreasing on closed interval a comma b. So now let f is increasing on, let f is increasing on closed interval m. What is an increasing function? F of a is less than or equals to f of x is less than or equals to f of b, right? For all x belongs to a comma b. F of a less than equals to f of x less than equals to f of b for all x belongs to a comma b. This implies f is bounded on closed interval a comma b. So as it is bounded, we have to prove it is Riemann. So to prove Riemann, first we have to be defining the partition. So let P is equals to A equals to x naught, x1, so on up to xn is equals to BB partition. This B partition on closed interval A comma B such that delta R is less than epsilon by f of b minus f of a. So why are we writing all this? Because we wanted it to be strictly less than epsilon, where IR is equals to xr minus 1 comma xr. This is the closed subinterval. Let MR be supremum. Let MR be supremum of f on IR. Let this be supremum on f on IR and small mr be infimum of f on IR, the same rth subinterval. So what is m? M is equals to f of x1. And sorry, as we are defining on this, the capital M will be M equals to f of r and small mr will be f of xr minus 1. So we got to subtract this 2. So what is that you will get if you subtract mr minus mr, that is equals to summation, sorry, you have to first, as we are talking about Riemann integral, you will be writing what is that we have defined. Capital MR is equals to f of xr and small mr is equals to f of xr minus 1, right? So from this we can tell that capital MR minus small mr is equals to f of xr minus f of xr minus 1, right? So what is Riemann integrable? UPF minus LPF should be less than epsilon. So we got to define that UPF minus LPF, that is equals to summation r equals to 1 to n capital MR into delta R minus summation r equals to 1 to n small mr into delta R. If you take delta R common, you will be having summation 1 equals to r equals to 1 to n capital MR minus small mr into delta R. So what is this summation r equals to 1 to n? What is capital MR minus small mr? We have written this as f of xr minus f of xr minus 1 into epsilon by f of b minus f of a. This is since from 1. Okay, now we will define this one. So how will you define? Strictly, as this is without r, I'm writing it out. Epsilon by f of b minus f of a into f of x1 minus f of x naught plus f of x2 minus f of x1 plus so on up to f of xn minus f of xn minus 1. Till here you got to write. Next, this is strictly less than epsilon by f of b minus f of a into, you can write this as f of xn, like all these gets cancelled, f of x1, f of x2, and all the terms gets cancelled except these two. So f of x1 minus f of x naught. So what is f of x1 minus x naught? Epsilon by f of b minus f of a into f of b minus f of a. So this f of b minus f of a gets cancelled. So this is strictly less than epsilon. So whenever UPF minus LPF is strictly less than epsilon, we can conclude that f belongs to R over a comma b. I think I'm clear till here. We'll just look into the converse of this theorem. What is the converse of this theorem? If f belongs to R over a comma b, will f be monotone or not? That is either increasing or decreasing, monotonic or not. So to prove this, I will just quickly, give you one example. Let us take an example, that is f of x is equals to sin x. Obviously, sin x is a continuous function. By the graph, we will know that sin x is continuous on 0 to 2 pi, right? This graph will be continuous on 0 to 2 pi. So that f is Riemann integrable, because every continuous function is Riemann integrable. So that f is Riemann integrable on 0 comma 2 pi. But it is Riemann integrable on 2 comma pi, 0 comma 2 pi. But this is not monotonic. That is, it should either be decreasing or it should be increasing. But these both are fluctuating. The graph of sine pi will be like this, right? It will be something like this. So either it will be, what is the monotone definition? Either it should be increasing or it should be decreasing. So this is not monotonic. So clearly this is not monotonic. Okay. So this is the converse of the theorem. And in the next class, we will just go with definition of Riemann sum. And then you will be having a very, very important theorem, that is fundamental theorem on integral calculus. So we'll just look at those theorems in the next class. And thank you.